Good morning, students. Chapter 2 continue, and it is almost last theory of this chapter. Energy stored in a capacitor. See, we know that why capacitors are used. Capacitors are used to store charge. To store charge. Now, how to store charge? We know whenever we put charge on an object, we have to do some work, and that work is stored as its energy. The same concept we will apply here. Okay, capacitor means we will have two plates. On two plates, on one plate we have to store positive charge, on another we have to store negative charge. So work required to put this positive and negative charges on these two plates is stored as its energy. Okay, what is situation? See here. Consider initially two uncharged conductors 1 and 2 as shown in this figure A. Conductors 1 and 2. They are initially uncharged. Charge on this plate 0. Charge on this plate is 0. Now, what is process? What is method? We will bring charge from this conductor 2 to 1. From this conductor 2, we will bring positive charge on this plate 1. Yes or no? Yes. So this plate, it becomes positively charged gradually, and this plate will become negatively charged. Clear? Okay. What is process? Initially, these two plates are uncharged. Means total charge on this 0. Total charge on this is 0. We will transfer charge from plate 2 to plate 1. Okay, see. Now imagine process of transferring charge from conductor 2 to conductor 1 bit by bit, so that at the end conductor 1 gets charge plus Q, and by law of conservation of charge, conductor 2 has charge minus Q as shown in this figure C. As shown in this figure C. Okay, we want to store charge on this plate plus Q. So on this plate it will be minus Q. Why? Minus Q. Plus Q and total charge will become 0. Because what is total initial charge in this case? 0. It is intermediate situation. This figure B is intermediate situation. And from this we have to find work done. See, initially charge on plate 0. We transfer charge from conductor 2 to conductor 1. Okay, from conductor 2 to conductor 1. Let at some intermediate time charge on this plate, conductor 1 is plus Q dash. So what is charge on this? It is minus Q dash. Now, during this, if I transfer daily Q dash charge from negative plate or conductor 2 to conductor 1, then yes, see there is positive charge. Del Q dash, positive charge. We know that this del Q dash charge will experience impulsive force, and this charge will not move by itself. Means to bring this del Q dash charge from conductor 2 to conductor 1, we have to do some work. Clear? Again, initially these two plates are uncharged. Step by step, we bring charge from conductor 2 to conductor 1. At some intermediate stage, charge on this plate is Q dash. On this plate it is minus Q dash. And now if I am taking del Q dash charge from conductor 2 to conductor 1, we know that against repulsive force, I have to do some work. So how to find this work? Okay, first of all, we will find work to transfer this del Q dash charge, and then to transfer all Q charge, we will take its integration. Okay, so see how to write it. Consider the intermediate situation when conductor 1 and 2 have charges Q dash and minus Q dash. In this situation, what is potential difference between them? V dash is equal to Q dash upon C. We know this equation. Okay. Now, if a small charge del Q dash is transferred from 2 to 1, work done in this step dW, resulting in charge Q dash on conductor by increasing Q dash to del Q dash. Q dash to del Q dash. What is charge on this plate? Q dash. Now if we bring charge del Q dash, then what will be charge on this? Q dash plus del Q dash. And on this, minus Q dash minus del Q dash. Okay, so what is work done during this transfer of charge? dW is equal to dQ dash V dash. Now what is this equation? Hello, it is nothing but W is equal to QE. It is nothing but W is equal to QE. dW to transfer dQ dash charge from conductor 2 to 1 is dW is equal to dQ dash V dash. What is value of dQ dash? As it is V dash, it is Q dash upon C. So it is work to transfer charge dQ dash. Now if we want to store charge Q, what is initial charge? 0. What is final charge? Q. So in building charge plus Q from 0 on conductor, total work done, W is equal to integration W. Okay, integration dW. What is integration dW? dW means work required to transfer only small charge, another small charge, another small charge. Then how to find total work done? W is equal to integration dW. If you put value of dW, it is Q dash upon C del Q dash. Integration is with respect to charge. And what is limit of charge? 0 to Q. Because initial charge on plates is 0 and final charge we want plus 1 upon C constant out of integration. Q dash del Q dash. What is integration of Q dash? Q dash square by 2. If you put upper limit and lower limit minus lower limit, then you will get W is equal to Q square upon 2C. You will get W is equal to Q square upon 2C. Yes. So energy stored in capacitor, work done is stored as energy stored in capacitor, U is equal to Q square upon 2C. Clear? Now as for capacitor, we have three variables C, Q and V. We can write this equation by three method. Okay, by three terms. It is in terms of Q and C. Okay, now how to obtain this two equation? You know one relation, that is C is equal to Q upon V. First of all, put value of Q here. Q is equal to C. Q is equal to C. Then you will get half CV square. Then put value of C. Then put value of C. You will get this equation. In this equation, first of all, put value of Q from here, C. And again, to obtain this equation, put value of C. So there are three equations. Based on data given, you can use any of these equations. Clear? Okay. Now last point is energy density. What is energy density? Energy density is energy per unit volume. It is defined as energy per unit volume. In capacitor, see here, in capacitor, this energy is in terms of, in form of electric field. Remember students, in capacitor, energy is stored in form of electric field. In form of electric field. Okay, so it is denoted by rho E, energy density of capacitor. Energy half CV square upon volume. What is volume? AD, because cross sectional area of capacitor A, distance between them D. Then what is volume? AD. Now to put value of C, epsilon 0 A upon D. Then C, this A cut. Now it is C half as it is, epsilon 0 as it is. V square upon D square. V upon D, it is E. So V square upon D square is equal to E square. So it is equation of energy density of capacitor. Pause your video and write down from bottom. Okay, so now one question based on potential energy. What is given? Parallel plate capacitor having area of each plate 90 centimeter square, separated by 2.5 millimeter in air as medium, charged by a battery having 400 volt supply. First question is, what is potential energy? What is energy stored in capacitor? We know its equation, U is equal to half CV square. Okay, V is given, you are not given C. How to find value of C? C is equal to epsilon 0 A upon D. Easy. So U is equal to half CV square is equal to half epsilon 0 A upon D into V square. You know each and every value. Yes, you have to convert this centimeter square in meter square, millimeter in meter. Second question is find energy density. Hello, what is energy density? Energy density is energy per unit volume. Energy you have found in equation question number 1. Volume, it is A into D. Clear? So it is one very simple question based on potential energy, based on energy of capacitor. Now, as homework, you have to solve 10 questions for series and parallel connection. It is for your homework. You have to think from your side. Okay, which capacitors are in series connection, which capacitors are in parallel connection, how to apply rules. See, question is common. Find equivalent capacitance between points A and B. 1, 2, 3, 4, 5, 6, 7, 8, and 9, 10. Find equivalent capacitance and send notes on my WhatsApp number. Okay, try. Just to try how to solve such circuits, how to find equivalent capacitors. Okay.